Hey everybody, Dr. Retzik here. This is our intro video to section 15.5, where we make the leap from double integrals to triple integrals. Let's get started. So what we want to do is continue to think by analogy initially. So let's talk about how the idea of integration has evolved for us since Calc 2. So you got the Calc 2 version, quick and dirty. You got some function, y equals f of x. The region of integration is some sort of closed interval down there on the x-axis. And you're interested in area under the curve, and the way you start to get your hands on that is you break your region up into a bunch of little subintervals, and you use those as the base of easy objects, rectangles. Okay, great. Now we used that idea to leap into double integrals. So section 15.1, say, this very quarter, where now it's 3D space, x, y, z coordinate system. It's no longer a function graphed as a curve, but now rather as a surface. So let's say z equals f of xy. And we said, okay, well, let's keep thinking of this as being defined over some region flat in the xy plane. We kept shading in those regions like this. Call that region R, and we would break our region into a bunch of subregions. Now back in Calc 2 it was subintervals. Initially here in Calc 4 for double integrals it was subrectangles. And each of those served as the base not of a rectangle, but rather of some sort of rectangular column. And we computed not so much area under the curve, but volume under the surface. Okay, make the leap. We want to start thinking about triple integrals. Now, the notation, I guess, is going to look like this. So we're going to have the triple integral of a function of 3 variables. Now, in the olden days in Calc 2, integrals were done dx, where dx represented a little bit of length in the interval of integration. And then for double integrals, we integrated with respect to area, where the dA represented a tiny bit of area, flat in the region in the xy plane. Now, the domain of our function is itself some region E in 3D space. So maybe E looks like this. Maybe E is like a solid brick. So here's the region E in 3D space. So it's all of this. It's this solid object. And if you think about what you would break this solid object up into little sub-objects, okay, well back in Calc 2, the sub-objects were subintervals. A few sections ago in Calc 4, the sub-objects were subrectangles. Now, they're going to be sub-boxes. So you're going to think of this thing as being broken up into gazillions of little sub-boxes. And those sub-boxes serve as the base of some sort of hyper column, some sort of four-dimensional column where that sub-box in red there is the base, and the height is given by the function f of x, y, z, and is pointing in some direction that I can't depict on this iPad. In any case, you might be willing to call the little subpiece not dx, not dA, but dV. And so here in 15.5, we're integrating with respect to volume. So in principle, that's the analogy. In practice, we got to figure out how to deal with some version of Fubini's theorem where we can turn these triple integrals into triple iterated integrals. And that's going to have us considering 6 different orders of integration: dx dy dz, dx dz dy, dy dx dz, dy dz dx, dz dx dy, dz dy dx. We got a lot of options, and some of them may be preferable to others. The first thing we want to do, though, in today's video is just look at a concrete example and see if we can set up limits of integration. All right, here's the example. Let's consider the triple integral over some region E of some function. The function itself doesn't matter for this example. We're interested in this example in simply turning the triple integral with respect to volume into a triple iterated integral. So now they have to tell us what E is. Otherwise, we couldn't be specific about our limits of integration. So consider that triple integral where E is, and in this one, they're just going to give us a picture. So we don't have an analytical description of E. We have only a picture, and the picture goes like this. It's actually looks a little bit like a skateboard ramp, a quarter pipe. I had one of these growing up when I was little. So like this. That is the region of integration. So I'm going to shade that in. All of that 3D object, that's E for us in this example. Now, we got to be a little more specific in terms of where this object sits in 3D XYZ space. So this object actually sits like this. Here's the x-axis. Here's the y-axis. And here's the z-axis. So that's the region E. That's E. All right, now let's get super specific. This is x equals 1. And this surface here, the actual ramp portion of the skateboard ramp, is given to us as z equals y squared. Z equals y squared. And back here, this is y equals -1. Back there. And therefore, this is z equals 1. So that z equals y squared, remember, that's a taco shell like this. And we're looking at only the part of that taco shell that sits above a square like that. So that's this square here. So it's taco shell, but it's only the part that sits above a very specific 1x1 square in the XY plane. Okay, so that's the region E. That's what we got so far. Our objective is to turn the triple integral with respect to volume into an iterated triple integral. Okay, so there's lots of different orders we could choose from. I'm going to pick one randomly. We'll try to write down the limits of integration in that random order, and then we'll think about how our analysis might change if we change the order. So let's just try this one first. For no good reason at all, let's just try turn this into a triple integral of whatever the function is. Again, not important to this discussion. And let's go for the order dz dy dx. So that's the order we're aiming for in this one. Now, the key thing is, when you're setting up these iterated integrals, remember, whatever the outermost variable of integration is, the limits on that integral, that better be number to number. Like, you can't have letters in those limits of integration, because when you were done with the problem and had finally plugged in those outermost limits, if there were letters in there, your answer would have letters in it and would not be an actual number. All right, so let's talk about the x's that are in play in purple. Look with your eyes at the region and just ask yourselves, what x's are in play? And to me, I see these x's here. In this region, x runs 0 to 1. Okay, now, at each such x between 0 and 1, say right there, think about the y values that are in play for that x. So I see those right here. And from lesser to greater, the y values that are in play for that x are -1 to 0. They're independent of x. No matter what purple x we're thinking of between 0 and 1, the y's vary from -1 to 0. Okay, now, for any such x comma y choice, so pick an x between 0 and 1, and then pick a y for that x between -1 and 0, say you're here. For any such x and y chosen in that way, think about how z is going to vary. Z is going to vary from the ground, flat in this problem in the xy plane, from 0 upwards until you hit the skateboard ramp. And that skateboard ramp is governed by z equals y squared. So whatever x comma y you are standing at, z will vary from 0 up to y squared. And if you consider all possible points chosen in that way, x is in purple, y is in red for each given x, and z's innermost in green for each given x comma y, then you will have described every conceivable xyz constituting the region E. So if we go in that order, dz, dy, dx, those would be our limits of integration. Now, I will leave you with one thought. There are lots of other orders of integration. We could have gone dz, dx, dy. Or we could have gone dy, dx, dz. Or dy, dz, dx. Or dx, dy, dz. Or dx, dz, dy. 6 total orders. And depending on one's perspective, the limits of integration will be different. So let's entertain this notion. What if we went dz, dx, dy? The original limits in our setup don't make sense anymore because now we have to describe the region E, which I will redraw for reference here. The skateboard ramp. Through a whole different vantage point. Okay, so say we were focused on this one. This time the outermost variable is y. So the very first answer we have to give is what y's are in play. And you can see that the y's in play run from -1 to 0. Then the middle limit of integration in purple. For each choice of y between -1 and 0, we got x's running (0 to 1). And for any x and y chosen in that fashion, if we were standing at a particular x comma y chosen in that way, z would still run 0 up until it hits the rooftop, up until it hits the ramp. So z would still run 0 to whatever y squared is. So that order was pretty easy to switch. Instead of dz, dy, dx, we have dz, dx, dy. These just got swapped. And so the outer two integrals were affected, but the innermost integral wasn't affected because dz was the innermost integral in both. But there's 4 others, and you guys should try to set up all 4 before class on Thursday. Get your mind all turned around so that you can go in any of the 6 orders here in 3D space. We have a whole nother day on 15.5 because I think these problems, they take some time to come to grips with. And so we'll have another video where we do some more examples and 2 whole class days of discussion. But that's the intro. It's in analogy to double integrals, which were themselves in analogy to Calc 2. And now you just got to think in 3D instead of in 2D. All right, go practice. I'll talk to you guys soon. Bye.